superconductors. They're basically the holy grail of modern engineering. We've all heard the promises, right? Perfectly levitating high-speed trains, hyper-efficient MRI machines, zero-loss power grids delivering endless clean energy, the whole shebang. Yet, decades after their initial discovery, there's still this highly specialized, extremely expensive niche. Why isn't our world already running on this miraculous technology? Well, welcome to our explainer. Today, we're going to investigate exactly why high-temperature superconductors haven't taken over the world yet and unraveled a fascinating scientific mystery that's holding them back. Okay, here is our roadmap for today's investigation. We're logically tracing the bottlenecks, starting with 1. The superconductor paradox. Then we'll dive into 2. The atomic roadblock, and 3. The manufacturing nightmare. After that, we'll look at 4. Joints and cryogenic hurdles, 5. Economics, and finally, 6. The strategic path forward. We've got a lot of ground to cover, so let's get right into it.
All right, Section 1, the superconductor paradox, promise versus reality.
Okay, let's dive into this paradox. Back in 1986, the scientific community was turned upside down by the discovery of high-temperature superconductors, or HTS. To really get why it's a paradox, we need to contrast these two materials. Take traditional low-temperature superconductors, or LTS, like niobium titanium. They're ductile metals. Think of LTS like bending a metal spoon. You can draw them into wires super easily, and they have a large coherence length. The catch? They require a freezing 4.2 Kelvin operating temperature, which means you're relying on highly expensive liquid helium. Now look at high-temperature superconductors. The massive advantage here is an operating temperature of 77 Kelvin, meaning you can cool it with cheap liquid nitrogen. But look at its nature. It's not a metal, it's a brittle ceramic oxide, like Ribco. It's fragile, incredibly sensitive to defects, and anisotropic. If LTS is a bendable metal spoon, HTS is like trying to bend a ceramic coffee mug. This brittle ceramic reality is the very first clue in our mystery. Which brings us to Section 2, the atomic roadblock, the physics of misalignment.
To truly understand why a brittle ceramic is so tough to work with, we actually have to zoom way in to the microscopic level. The core issue here is something called the grain boundary problem. In traditional LTS metals, the boundaries between the microscopic grains of the metal are actually helpful. They act as flux pinning centers that stop magnetic vortices from moving around, and that actually increases the current density. But in HTS cuprates, the exact opposite happens. These grain boundaries act as severe weak link barriers. So instead of helping the supercurrent flow, they completely block it, shifting the material into an insulating or semiconducting state where charge carriers are basically forced to tunnel between grains.
Get this, it is unbelievably sensitive. A mere 45-degree atomic misalignment between adjacent crystals causes the critical current to plummet by 3 to 4 orders of magnitude. Think about what that actually means. Because the HTS coherence length is tiny, we're talking only 1 to 2 nanometers, even an atomic scale disruption completely suppresses that current. The destructive overlap of the wave functions basically shuts the whole highway down. If the atoms aren't perfectly aligned, your superconductor just becomes a highly expensive brick.
Moving right along to Section 3, the manufacturing nightmare, building a nanoscale layer cake. Because simple traditional polycrystalline wires just won't work with those unaligned grains, engineers had to invent a wildly complex workaround. They came up with second-generation coated conductors. Let's walk through this insanely precise architecture. It's basically like baking a highly fragile nanoscale layer cake. First, you start with a flexible metal substrate, something like Hastelloy, just for mechanical support. Second, you deposit a series of buffer layers to stop metallic atoms from bleeding into your superconductor, and crucially, to create a perfect crystalline template. Third, using vacuum deposition, you grow a 1 micrometer thick superconducting REB colayer that perfectly copies that aligned template. And finally, you cap the whole thing with silver and copper to stabilize it electrically. Every single layer has to be absolutely flawless to force those ceramic grains into perfect alignment. But here's the catch with this engineering marvel. It is incredibly fragile structurally. When you try slitting these wide, multi-layered tapes into narrow wires, it can create up to 100 million microscopic edge cracks per millimeter in the buffer layers. And when you actually put these tapes into real-world high-field magnets, the massive Lorentz forces can cause the layers to literally peel apart and delaminate. Or, say a localized hotspot forms during a quench, the thermal expansion will crack that brittle ceramic layer right down the middle, causing permanent damage. It's a real nightmare. Next up is Section 4,
joints and cryogenic hurdles, the resistance barrier.
Now, let's say you've actually managed to manufacture this delicate tape without breaking it. You still have to connect these tapes together to form large, persistent magnetic fields. Now, what's really interesting here is how it perfectly explains why your local hospital's MRI machine still uses older, expensive-to-cool LTS tech. To operate efficiently, an MRI magnet has to run in persistent mode, meaning the current just loops endlessly without a power supply. That requires a joint resistance of less than 10 to the negative 14 ohms. You can achieve this easily by cold pressing older LTS materials. But HDS? If you try to solder REBCO tapes together, the tin in the solder reacts poorly with the ceramic, leaving you with way too much resistance. Because of this, HDS magnets usually have to run in driven mode with a constant, highly stabilized power supply, which introduces a ton of heat. And speaking of heat, what happens when you try to use these HTS tapes for alternating current in power grids? Well, because the tape is essentially a wide, flat ribbon with a crazy 10,000 to 1 width-to-thickness ratio, pushing alternating current through it generates massive magnetic friction. These are known as AC magnetization losses. There's a massive disparity here. The heat generated internally by these AC losses heavily outweighs the environmental heat leaking in from the outside. That entirely overburdens the complex liquid nitrogen cryocoolers, which already struggle with long-term reliability for massive utility grids.
All right, shifting gears to Section 5, Economics, the Market Catalyst.
Let's pivot and see how this all fits into the broader macroeconomic landscape. Engineering hurdles aside, strict financial realities are keeping HTS out of the mainstream grid. Mature, easy-to-manufacture LTS costs about $1 per kiloamp meter. HTS, on the other hand, currently sits anywhere between $80 to $230. That's purely because of that highly complex, low-yield vacuum deposition process we looked at earlier. To even be competitive for widespread power sector use, the HTS industry has set a massive target for 2030, dropping that price all the way down to roughly $10. Finally, Section 6, the strategic path forward, engineering the cure. No, the outlook might seem pretty daunting, but it's far from hopeless. Let's look at where HTS is already succeeding today and how engineers are actively curing these bottlenecks. In specialized arenas where extreme performance is absolutely necessary, HTS is already justifying its steep costs. Take fusion energy, for example. Companies are using HTS magnets to enable highly compact tokamak reactors, like the Spark and Arc designs, producing magnetic fields over 20 Tesla. That's something entirely impossible with older LTS materials. Likewise, in high-speed transportation, advanced SC maglev rail systems in Japan and China are using superconducting tech to achieve 30 to 40% greater energy efficiency than conventional high-speed rail, all thanks to zero rolling friction. And for the rest of those technical challenges, the engineering cavalry is attacking them head-on. To solve those massive AC heating losses, engineers are actually using laser striation to slice the superconductors into tiny filaments. To fix the thermal cracking from quench risks, they're developing no-insulation winding techniques that drastically improve a magnet's ability to survive localized heating. And to bring that staggering price tag down toward the $10 mark, the industry is rapidly scaling up continuous reel-to-reel chemical vapor deposition to finally mass-produce these materials. So the physics of the green boundary might just be an unchangeable quirk of nature, but human engineering is adapting around it, layer by microscopic layer. Thanks for joining me on this explainer, and keep learning.